Okay, so this talk is based to a large extent on work that was done with Jerry Marsden over the last 15 years or so, especially on the shared geometric properties in the analysis of fluid flow, which we used to work on, and shape analysis and shape transformations, which we then started working on later. But many other collaborators have provided inspiring ideas and help in doing this. The talk is going to discuss some of the uses of geometric mechanics in shape analysis. Shape analysis is the word that we just sort of describe for what is suggested to us as geometric mechanics when we see the computer scientists processing images. So we'll talk about some uses of geometric mechanics in the shape analysis, and I'll give you one case of an example, and I'll try to give you, like Matthew did, give you several vignettes of applications, and some trade secrets will be revealed. I'll reveal them right away. Okay. So the need that for image analysis, shape analysis, this approach in geometric mechanics comes up because large numbers of images, all kinds of different images with all kinds of different imaging machines are being developed rapidly, and lots of images are being produced. Doctors won't have time to go through the microfiche or whatever they are to study the progress of their patients. So one of the things we want to do is develop this concept of the computational anatomy. So that these images will be taken, and then a computer will analyze the images, and we'll tell it what to look for, and then when it finds something, like a change between an MRI 3 months ago and an MRI this month, you say, well, you should look at that. Yeah. So changes between two images is one of the things we're going to be interested in. So here are the various operations that people think about. One is just image registration using data structure of just brightness or intensity. That's the usual black-white X-ray sort of thing you see. Another is the curve and landmark registration, which is a newer thing, where you think about how the cartoon of the image changes, just thinking about drawing around it, or points on the image called landmarks. How do they move? Going from one MRI, say, to another one. Yeah. Okay, so I had a really interesting postdoc who could do geometric mechanics, could write code, and he is also working with the computing science guys. Okay, so I'd send him over as a spy, okay, and ask him, find out what those guys are doing, and we'll come back and explain it to us, and we'll try to formulate it our way. Okay, so one of the things they wanted to do was data fusion. So you take images of one kind, say MRI, another kind, or maybe even functional MRI, another kind, say, that measures directions that muscles point or something like that. But you want to get them into the same analysis. Okay, that's called data fusion. Another one is multi-resolution. Some parts of the image are more important than others. So the resolution doesn't have to be uniform across. And an important one is longitudinal studies. We have, for example, one of the studies being done at Imperial College is a study of MRIs of brains, starting with infants. In particular, they're studying premature babies. to see whether there's a difference in the shape of the brains as the brain develops over 20 years, because premature babies tend to have learning difficulties and they have disadvantage because they're not still hooked to their mother's endocrine system, when they have to leave early. Anyway, this study has really been intriguing me for a long time. It's going on for 20 years, okay, and it's going to have hundreds of babies, and there's lots and lots of data. So this, and those are called longitudinal studies. And something like Fatima was talking about yesterday, we'd like to have run splines through those images, because that's not the way biology works. Biology doesn't just evolve for a while, you take a picture, and it evolves in a different direction. Right? So you have to have all the pictures, and you have to go through all the data. So you want splines that'll do the shape analysis for you. And then, of course, there's this issue that's very common in this field of atlas building, where you try to build, discover from a big data set what is like a normal heart. What does a normal heart look like? And then how far away are the individual patients' hearts from being normal? I mean, if the computer can measure that, that's really useful information to pass on. But that introduces the idea of statistics of images, and these images are actually described by maps. They're not described by some linear process. And so there's an issue there that's worth considering. Or transform the representation of the image to a vector space. Then you can do statistics. And finally, on this list here, there's the effect of noise. There's noise in the scanners, and there's noise in the process of growth, where you start out with an image, and something between the two times you took images changes and grows, and you actually will see different topologies, for example, on the two images. And that's something that should be called forward to the doctors again. Something changed. Okay, how about this one? This is what they're doing, and even more, of course, but these all offer interesting challenges to geometric mechanics. And our response needs to be effective. I mean, it needs to be general and flexible. It needs to incorporate new needs as things develop. And in particular, it needs to be able to adapt to new types of data structure. Okay, it's a big order, but it turns out that this problem was just meant for geometric mechanics. Okay, there are many people who have collaborated with me in this work. Maybe you know some of them. There's Martins, Colin, Francois, Jerry, of course. I have student David Meyer, Lyle Noakes in Australia, and I think Fatima mentioned him yesterday. Tudor, Laurent Rieser, Alain, Joris, FX, and Laurent Jonas. Okay, these are all people we've written papers with, collaborators on this in the past 10 years. Okay, so trade secret number one for the geometric mechanics of shape turns out to be watch for momentum maps. Once you cast it into the form of momentum maps, you've got it into a framework. So these momentum maps provide a powerful organizing principle, and they're central for this endeavor. And of course, they arise from any lead group action on a manifold, and they don't have to be symmetries. They just have to be able to understand how they evolve using add star. Okay, in particular, we're going to want equivariant momentum maps, which evolve by add star. Okay, trade secret number two. We take a Lagrangian embedding viewpoint. So this is one of the things shared between fluids and shape analysis. There's a Eulerian picture and a Lagrangian picture. If you can take a Lagrangian embedding viewpoint, then you concentrate on moving the Lagrangian part of the image, like some outline, instead of moving the entire image all over, right? Deforming the entire, because it's another whole dimension smaller if you're only going to be moving the boundaries. You don't have to move everything of the ambient space. Okay, so linked with that is trade secret number 3. Okay, so it's when you're matching shapes, and we'll talk about this example as a shape regarded as a continuous embedding in an ambient space, like an S1 embedded in an R2, just closed curves in a plane. So if you unreduce by the inverse of the momentum map for left diffeos, you go back from the Eulerian to the Lagrangian picture, and that can be very helpful because the boundaries are moving like Lagrangian variables. Okay, so you can analyze now how the boundaries move instead of how the entire domain moves, and then come back down. I'll show you how this works. And the fourth one, and the one that Deb just referred to, is this idea that you can develop intuition for control problems by thinking of what's happening with the initial value problem, the flow problem. And one of the bonuses for that is that problems like trying to match two shapes, if you just turn them loose as initial value problems, turn into have beautiful confined wave structures and interactions of those wave structures and development of singularities in finite time which interact with each other. So this is a little equation here. It's the Euler Poincare equation. In the case when it's just diffeomorphisms acting on H1 on the real line, produces soliton equations. And the structure of those soliton equations expands into any number of dimensions. Okay, it produces it by just Hamilton's principle for a Lagrangian, which is the square of the H1 norm. Okay, so I'll say a little bit about shape change and fluid flow, what motivates us. I'll talk about fundamentals, which everyone here already knows about, but I just want to hook them together with this problem. I'll talk about two applications in the most workhorse application. The common applications are curve matching and image registration. And if I have time, I'll talk about other applications, multi-resolution, data fusion, change of topology, and maybe at the end I'll get to geometric splines, which is a counterpart to what Fatima was talking about yesterday. Okay, so we can imagine that a fluid flowed into the shape, and shape changes, and we can imagine that the shape analysis then will also be related to the flow of shape. And the difference between these two images, that image and this image of the cortex, is that this one has colors on it, and the other one is just a shape. The shape defines the boundary. So it turns out that geometric analysis, geometric mechanics summons another degree of freedom in order to match shapes. It's a controlled degree of freedom, and it's the momentum of the shape. Because remember, we're going to lift things back up into a cotangent bundle, so we need to have the cotangent lift. That produces an extra description of the shape, which is not just its position, its outline, but its momentum. And it's like knowing what the normal vector is to the shape, but it's different. It's not a velocity, it's a momentum. Okay, so this all began at the end of the 19th century in the study of morphology, the comparison of biological shapes. Especially this guy Darcy Thompson, he would take a fish, flop, right, and he puts it on a piece of graph paper, right, and then he stretches the graph paper, does some kind of simple transformation of the coordinates, and then he redraws the fish. And he says, look, see the correlations of the various fins? These two species must be related somehow. Okay, so he had a beautiful way of saying this, just quoted many times. A very large part of morphology, our essential task lies in the comparison of related forms rather than in the precise definition of each. And this process of comparison or recognizing in one form a definite permutation or deformation of another lies within the immediate province of mathematics and it finds its solution in the theory of transformations. So a few pages later in this book, he tells us that he learned of it from Henri Poincare. Okay, so here are some more of his drawings. These fish, and vertically one above the other, are supposed to be related, and they are related. Those pictures are related by stretching the whole space. Okay, and they, you know, and look at this. See, they even have the names of the fish. Okay, now this is what I was saying about sequences of images. Here's the brain of a 1-year-old infant. This is a cortex picture. It's a MRI, which takes a slice. And then at 2 years old, no, so this is a baby. This is, oh yeah, and think about this. This is the baby that's just been born. 15 weeks before that, the cortex is like smooth as a basketball, just round. And then this development begins, bending in the cortex and changing the shape begins. And it keeps going, actually, until for the first 20 or 25 years of a human being's life. So when you see a teenager, don't worry, brain's not developed. You know? Okay. So here's a question. What is the geometric mechanics of shape analysis? And it starts from people saying, well, how could ideas from mechanics and fluids help develop shape analysis methods for image registration? And of course, Darcy Thompson's answer was transformation theory. And I think it's a good answer because it leads to momentum maps. And the evolution of the momentum maps, here's the differential equation for them. By add star, just it is the equation we need. That's the equation for relating two shapes as they're evolving. Okay. So I remind you of the Euler-Poincare formulation of this. You write the Lagrangian on the tangent bundle, and then you take the variational derivatives. That puts you in the cotangent bundle, and the variational derivatives with respect to u drop you to the dual of the Lie algebra. Okay, so this is the Euler-Poincare equation, which is another way of writing add star or coadjoint evolution. Okay, and this is a very common equation. The Euler-Poincare equation appears in all the things we teach, right? The rigid body, the ideal fluids, and this is the general form of it, where here m is the variational derivative, m is the momentum map, and this is add star when m is dual to vector fields, and so m is a one-form density. That's what add star looks like. And then it also appears in the optimal control problems as not as initial value problems, but as boundary value problems. And here's an example. In fact, one of the things I was thinking about when I asked the question earlier about non-holonomic control problems was thinking maybe, instead of forcing a particular evolution, you would just put in here a relationship, the non-holonomic constraint, okay? But you wouldn't add it as a constraint. You just add it as, like Deb was showing earlier, as a penalty, okay? So that you would then, as your tolerance goes to 0, then you get back to this hard constraint. But in the meantime, you're relaxed about this non-linear, non-holonomic constraint, and you're able to take variational derivatives of it. Okay, so that, and that's the right thing to do. Take the variational derivative and then take the limit. So I don't know if that idea will work. Okay. So, okay, I'm only going to show you this for one reason. Of course, you know what a cotangent lift momentum map is, and that you know it's equivariant, and you know that these are the equations on the phase space for the tangent and cotangent lifts. It turns out these equations appear again and again in different guises. Okay, so here's a point that makes a difference between fluids and shape analysis is that they have different momentum maps. Okay, the momentum maps of fluids are just diffeomorphisms of a region. And, well, the motion is flow is by diffeomorphisms of the region. The left action moves the fluid around, okay, and it is represented in the Eulerian description as momenta on the dual of the vector fields in R3. The right action changes the labels, believing the fluid's stationary, not moving. So that's what, for example, steady flows do. A steady Eulerian flow is moving the particles around, but the velocity is not changing. Okay, and this leads to the other representation of fluid dynamics called the convective representation. Upstairs here is the Lagrangian representation. Okay, so, and there is this other feature that Alan introduced and made famous, is these guys here form a dual pair, and Francois and Cornelia showed, well, it's a weak dual pair in some sense. Now for shapes. Shapes have been a different dual pair because they have different actions. So we want to define a shape not as just a set of points in a reference points or something in a space, but rather we want to define a space, a shape as a continuous embedding. And now here we're going to be doing closed curves in plane. That's a shape. Okay. You can think about it. It's really fun. Think about all the possible ways of defining a shape. You know, and what goes into the shape, texture and stuff. We earlier saw a picture of Lena in one of the talks, you know, and she has all kinds of texture in the picture. So it's more different data structure for the different parts of that photograph. Some of it is just blank almost, not changing much, with very little variation, and other part of it has fine texture. Okay. So now the same thing happens on the left. The left action changes the shape. Okay, it's going to think of a curve in R2, and when you act on R2, right? R2, that part of the map, it bends the whole space around, and it carries the shape with it. Now, so the embedding is like a Lagrangian curve. And when the flow of the volume changes, it changes the shape. Okay. On the other side, the right action acts on the parameterization of the curve, of the closed curve. It just reparameterizes. It doesn't change the shape, but it changes. It allows you to do, you know, any reparameterization. And the fact about it, which is nice, is that the left and right actions commute, so you can be reparameterizing as you go along. Okay, if you're trying to make the momentum map here, the J-Sing, which I'll tell you more about, evolve in time, or control it. So the momentum maps for Lie group reductions by left and right actions govern something called landmark registration or curve registration, because like I said, you could have a curve that defines your shape, and you could just put points in that curve and then move the points around, and those would be called landmarks. Okay, so let's look at an example. This is the example of morphing a U into an O into a U. And Colin Cotter wrote a paper for my birthday where he morphed a D into an H. You know? Okay, so how do you do this? It's going to start in some circular form, and it's going to be mapped into the U shape. And you can see that the reference coordinates are going to be moved around. So this is a change by the left action of the diffuse. And so here we go. We're going to run a little animation. You can see the reference points moving around as this approaches the U. And the difference between these two shapes can be thought of as a length. You want to quantify it, remember, so the computer points to it. And you can quantify it with all kinds of different norms, depending on what you want the computer to look for. And so we would like to be able to determine these geodesic paths, and we'll think in terms of Lagrangian paths between shapes on the plane, the ones we just saw, embeddings, S1 embeddings in R2. Okay, so we define our paths. Okay, there's some element Q that's going to define the boundary, and it's going to be associated with the velocity U, and Q composed with U gives the time rate of change of the curve. U is called Eulerian velocity in fluids, and dq dt is called the Lagrangian velocity. So you define some norm, and the norm will pick out what you're interested in about the image, and then that's up to your choice. Define some distance, and then try to find the distance minimizing geodesics when you go from the initial condition to another condition, the condition you're looking for. And then it's possible then to reparameterize to optimize how you are resolving the features you're interested in on the image. Okay, so that means modding out to make an equivalence class by all the reparameterizations on the space of continuous maps. Yeah. Uh-huh. But you're not doing all of, every time you do the whole thing. But you're not doing R2. You're just moving the boundary, the Lagrangian one. So it's a one-dimensional thing. Or you're only moving a finite set of points on the boundary. But the points might all converge to the place where the highest curvature was. And then you'd like to be able to, well, an equivalent shape would be having the points somewhere else but the same shape. So you can just reparameterize those points. You don't want to have like no points in some region that are not changing much. Okay, so this is the shape space, and this is the configuration space. Okay, so we call this modus operandi unreduction. Okay, so we're interested in a shape down here among these shapes, this family of shapes. But we lift back up to the Lagrangian picture. We evolve the momentum map. We have to know what momentum map to evolve. And then we project it back. Okay, so we need to look at the left and right transformations of our space. They commute with each other, like I said, and the left action corresponds to G composed with Q, and the right action corresponds to, well, that's moving the shape, and the right action corresponds to relabeling Q. So it doesn't move the shape. That's what gives us our separation of these approaches. And then they also have momentum maps, right? So the left action momentum map is this. This is the momentum map that first appeared in the water wave equation that had singular solutions, and the solutions went straight to this representation, this form. And Jerry and I describe this as the momentum map for left action of the diffeos on the image, and the image being an embedding. Okay, so this momentum map obeys the Euler-Poincare equation. There's M, that's our momentum map. It's preserved by right action. You can put just points on the singular distribution and just define them as landmarks of the shape. And then paths are governed by the Hamiltonian equation for the momentum map, right? This is what we looked at before, Q dot and P dot, the tangent lifted action and the cotangent lifted action of the left action of the diffeos on embeddings, continuous embeddings. Now, oh yeah, this is important because now we come to this control feature of the problem. Okay, so what is it? We know this, so far it all looks like an evolution equation. Okay, but in order to find the optimal path, say, of these points on the curve from one image to another, you use a shooting method, okay, in which you choose an initial momentum. Okay, you integrate it from time 0 to time 1, and darn, that's not the target. So you linearize along the path that you took, use the adjoint equation to integrate back to your initial condition, and you'll be at a different initial momentum. And then you shoot and iterate this until you get as close as you want, and you define a tolerance for how close you want. And that's an easy thing to do, and it's very quick, especially if you only have a finite number of points to match. Okay. So it turns out the momentum map for right action is very useful. It simplifies the solution. Everything is invariant under it, right? So it's conserved. Here's the cotangent lifted mapping. Here's the momentum map. It's minus P dq, okay, defined on the curve. P's and Q's are these Lagrangian variables on the curve. And we can write that as P dot dq ds, and we can then set it to 0 because it's conserved. And that will mean that the momentum is perpendicular to the tangent. So the only direction for the momentum is in the normal, and that means that our control parameter has dropped down to being a scalar. Okay, so it's very fast for finding the optimal path. Okay, so then now we understand what this picture told us. It told us that this was the shape that we came to, and in order to get to that shape from an earlier MRI, say, these are the values, the scalar values of the normal momentum, initial momentum that had to be introduced. And if you introduce those, then you'll go coasting smoothly over on the geodesic from the initial to the final shape, from time 0 to time 1. Okay, so cotangent lift momentum map is important in both fluids and shape analysis. You know what that PDQ is, by the way, for fluids? For those who know these things, that's the Clebsch representation of the momentum. So, that's an essential feature for fluids. It's also the thing whose integral around a loop is preserved. Okay, and that's called Kelvin's theorem, Kelvin's circulation theorem for the fluid. Okay, so there are 2 points so far. The geometric flow form of shape analysis summons momentum maps, and momentum maps. And the second point is this question of what can mathematics do for shape analysis has been answered with, look what shape analysis can do for mathematics. Okay, this is the second example, all in this slide. And it's very important because it's the typical way that images are analyzed. Just as a scalar intensity, which is like an X-ray, just white on black. And white is the intensity. Okay, so in order to register 2 images, to see how far apart they are, you think of the images as being in the smooth maps from the domain into some vector space. The vector space is the data structure. Okay, in this case, the data structure is they're just scalar functions. Okay, so we want then to minimize this cost function and to within some tolerance sigma over the evolution along the geodesic for the cost function. And if you do the optimization by taking the variation, setting it to 0, you get the momentum map. And this momentum map is the new thing. It's both new and old, actually. For scalars, so now you have to go back to Laurent Research. I wanted to go on to the next interesting thing about geometric mechanics. But he's working with the computing guys, and he's my spy. So I say, well, let's go on. He said, no, we have to do what they do first. We have to do the common garden variety algorithm. It's called the Begg algorithm, so that we know what to compare to. And we can say to the computer guys, see, well, yours is better. So I said, okay, I'm going home. I'm going to look at this Begg algorithm, which I never looked at before. And it's an algorithm thing, computer science algorithm. It involves Taylor series and asymptotic, and truncations. And on the other hand, it didn't take very long to know that looking at it from the viewpoint of the data structure being scalars, which is what it's for, that their algorithm was in fact a momentum map. Okay, and it was a momentum map, and so the evolution of the momentum map we knew, but in fact also it turned out that add came into this too. In taking the variation of phi at time 1, phi inverse at time 1, with respect to the velocity, okay, which is going to be phi 1 at time 1, you have to use big add. So your variational derivative for this momentum map involves big add. This is sort of kind of an encoding of it. It involves the map from 0 to t acting on the source image, and it involves the map from 1 back to t of this combination here, the difference, flat. Okay, so these two guys, this is in one vector space. These are scalars. These are densities in the dual space. And diamond is the map that takes you from V cross V star, vector space, and its dual vector space, into the dual of the Lie algebra. Diamond is, in fact, the expression for the momentum map, and even the one we've been looking at, it's P diamond Q. Okay, so this is the momentum map written in terms of the language of the images, and it does something for us. Now we can say, wait, I didn't want scalars. I wanted densities, intensities or something. I know, I wanted to have a little left-handed frame, okay? Or I want to have directors. I want to have something that goes on some order parameter. Or maybe I just want to have some coset space as my data structure. And all you do then is just do the calculation that determines diamond. Okay, and now you've got your algorithm. And here's how they use the algorithm. They use it as a gradient descent flow. They know that their momentum mapped to some operator on U. It came from taking the variation with respect to U there. And so they invert that operator. That's the thing that defines the norm, by the way. They invert this operator, put the Green's function, convolve it with J, and you know that guy, ut, is the right invariant velocity, so it's phi t dot and phi t inverse. And then you just iterate this from t equals 0 to t equals 1, and you relax following the gradient descent. And this little formula here allows you to convert matching of any data structures for images into a gradient descent equation. Yeah, this was when I was really stoked about momentum maps, because now there are two momentum maps which both were extremely useful. So then that's where I came up with this idea of watching for the momentum maps. Okay, so there's so much more to do. Remember the whole list from the SPY, about what the other guys are doing. There's this multi-resolution approach. And it turns out that the way you do that is with semi-direct products. Okay, and instead of having just one kernel for one resolution, you have a sum over different kernels for different resolutions that have different length scales in them. And momentum map for fusion of multi-component data structures, like we have some intensities over here and we have some left-handed frames over there, and we want to merge them in, to describe the information in one image, this data fusion method, well, okay, we just sum over the penalties or tolerances we had and do the momentum map for each type of tolerance. It's going to string out how long the momentum map is, but then that's going to just give you how you do your gradient descent. Okay, one I like, this is the one I was trying to get my SPY to work on, was this growth and change of topology under something called metamorphosis. And because I like it, I'll tell you a little about it. And it turns out to be related to interesting evolution equations. And then there's this issue about splines for actions of Lie groups on Lie groups and on Riemannian manifolds. That's this longitudinal study with all those babies, right, in the cortex. And then there's the last one, is atlas creation. And then the next 10 minutes, maybe I can do 1.5. So let me start. Metamorphosis was introduced by Alan Trevay and Laurent Jonas in 2005. And then 4 years later, we wrote a paper which is basically saying, oh, by the way, that's a momentum map. And so we have, it's a pair of curves in a group and a manifold, which could be another Lie group. Okay, and the parameterized by time. And the curve in N evolves by a transformation by G. So that gives something else in the manifold N called little n. Okay, and the quantities here, G and eta, are called the deformation part and the template part. So these guys, the N's are templates in which you feed your data. Okay, and then the G's are how you act on those templates. And if the etas are not there, or they're just constant, then you have this pure deformation we were talking about before. But if they are there, then this is an extension of what we were talking about before, basically to something like semi-direct product action. Okay, and this is what it can do. It can change topology. Okay, I'll show you the tolerance function for this. Metamorphosis allows for growth and change of topology. In fact, one of the examples was for this bird, it changes from a dove to a jay. At some point, any point we wanted to, we could put an eye into the bird, right? Change the topology. This one here is a change of topology. That's how we would put the eye in. Okay, so I want to look at a particular case where our cost function is going to be for scalar shapes, okay, with G acting from the right by G inverse, and our cost function is going to be the kinetic energy on the flow, and also this quantity nu with the tolerance on the templates. Okay, so nu is just how the template evolves under the action of the Lie algebra of vector fields. Okay, and so actually what we're doing is what I said earlier. You take nu, right, put it in here, minimize, think of this as the L2 norm, with respect to some sigma, calculate everything out, and your variations give you sigmas in some of the places. And see, we're not demanding that we satisfy diffeomorphic flow all the time, everywhere. We're only suggesting, okay? Like Debbie was saying, we have a tolerance, okay? If you don't want to be diffeomorphic for a while, that's fine, but it's going to cost. And so if we put that in there, a sigma appears in the equations, and we look at this guy here, M, our momentum map. Well, he is PDQ, of course, and the P guy is a momentum density. It has scalar density. It satisfies the continuity equation. And we can reconstruct. When we put these two equations together, then we get, and rescaled Z to take out the sigma. We can let M be any operator on U at this stage. But if we put the evolutions together with the momentum map, we get this equation here, which is the Euler-Poincare equation for a one-form density. And this piece here coming from the diamond part of the symmetric product. And then there's this auxiliary equation, which is the z equation scaled by sigma. Okay. So when you look at this equation, in the case where the norm is the H1 norm, here, in U, you discover something which is very interesting to me. Because if there's no rho, then this thing here is called the Holm equation, and it has soliton solutions, and it's been very well studied. When you put in the rho with the symmetric product action, then you add this guy, and it's still the shallow water equation. And now rho you can think of as the elevation of the wave. Okay, so now instead of just the waves moving because of flow, you've got also shallow water waves in the sense of the usual sense. This equation here, it's called CH21 for a reason. Or CH2 at this stage. This guy was discovered in 2005 or 2006. It's also completely integrable. It also is solvable by inverse scattering transform. So it's an interesting equation. Here's what it looks like for the solution. Yeah, this is rho, and let's see, and this is the velocity. In periodic domain, if you just make a lump, in the water, it spreads out, and it makes a series of solitons, which, for periodic domain, they go out like this, come back across, and you can see that they're nearly passing through each other. They collide, and there's some phase shift, and they continue. Okay? And the same thing in terms of the representation by velocity. Going to the left, keep going to the left, and then all these interactions are there. This is a classic soliton equation. Okay, so then let's do a little analysis. Still calling this thing CH21. I'll explain in the next slide why that is. You get this, you can write these equations as compatibility conditions for these two linear equations. These equations will be satisfied if psi xxt is equal to psi ttx and lambda, it's not changing. That's the spectral parameter for the psi xx equation. And mu, or m, while m is not a potential, m is something that's, because it's a non-local equation, it's actually an equation for a string. And this is a plucking the string problem. So this problem is bi-Hamiltonian, which is one of those things you use for calculating constants of motion, for example. And if you have it, and it's not very long before you can prove that it's completely integrable. But the bi-Hamiltonian one gives you infinite hierarchy of constants of motion and an infinite hierarchy of equations. But this one has no singular solutions. You have to make some slight change to get the singular solutions back. So here's the rest of the sequence. If you say psi xx is some operator depending on lambda on psi, and psi t is this combination, which is sort of copied down from before, and you ask what does this equation do when we take the compatibility condition for it, this is what comes out. And this is the Euler-Poincare equation on the Bott-Virasoro group in 1D. And then if you set Q equal to this sum over paths Q with powers of lambda, and U equal to sums over the U's with inverse powers of lambda, put that into this, then it generates the sequence for every choice of N and K of completely integrable equations. Okay, so here's one that Vakhtang Putkaradze did for CH2 minus 1. Okay, and it has the same flavor of the interaction of the solitons. Okay, so the second punchline is that the cotangent lift momentum maps in this shape analysis provide a unifying framework and their evolution equations. It's very interesting. Right? So this is the shared idea of dynamics and control theory. Since I come from the dynamics side, I had to look at the dynamics. Right? Control theory was like not, I didn't have any intuition. I had more intuition on the dynamics side. So I'll stop here.